Hello. The behaviour of particles in quantum mechanics is governed by what's called the Schrödinger equation, written here in its time-dependent form. So we sometimes call this the time-dependent Schrödinger equation, usually abbreviated to TDSE for short. So it was written down in 1925 by this man, Schrödinger. As you can see, a very well-dressed gentleman, as they were back in the 1920s. But you know what, it's the 20s again, so let's see if we can't conjure up a bit of that 1920s chic view in this video. It worked. Magic. Okay, so the Schrödinger equation, when Schrödinger originally wrote it down, was intended to be a classical description of classical waves. This quantity psi, which we call the wave function, was thought of as something like the wave function which would describe, say, water waves, in which case it would take some value which would tell us about the height of the water wave as a function of position and time. In fact, as we'll see, while there is a good description of the wave function as something like a classical wave, in fact quantum mechanics goes beyond classical physics, as we now, of course, know. Before we proceed, let me just make a couple of notational points. When I write d psi by dt like this is a partial derivative with respect to time, holding all spatial coordinates constant. So we can also denote this in the following way. Stating explicitly that the positions are held constant. Sometimes I'll denote this in a simpler manner in the following form, where partial subscript t is just shorthand for d by dt acting on psi, and sometimes I'll use Newton's notation psi dot. Similarly, partial derivative with respect to x implies that we're holding the other variables constant, so time, y, and z, which can again be abbreviated just partial subscript x acting on psi, and sometimes we'll write this as psi prime, where this last notation will only really be used in one dimension, where it's unambiguously a derivative with respect to x. So there are a couple of key assumptions we're going to make throughout this course. Let's just wipe this board off and write them down. When I say wipe the board off, of course, I mean magically clear the board. So let's write down some key assumptions. The first is that the Schrödinger equation is non-relativistic. It's going to describe the behavior of some massive particle in the non-relativistic limit. There are relativistic extensions to it, but we're not going to consider those in this course. The second is that we're only going to describe single particles. So again, there are extensions to the Schrödinger equation which will allow it to deal with multiple particles, but that's not going to be the focus of this course. The wave function psi always governs the behavior of a single particle. Okay, so let's take a closer look at what's going on in the Schrödinger equation. Let's clear the board again. Okay, so let's have the Schrödinger equation back. So we'll look at properties of the wave function psi in future videos, but for now let's just note that it's a complex valued function, and it has at the front of it an arbitrary global complex phase. So it's a mathematical redundancy built into the wave function that it has this global phase, which can be changed arbitrarily. It's a mathematical redundancy in the problem. But the relative phase between two different wave functions is important, and we will see that later on in the course. So, but for now there is this redundancy built into it. So let's take a look at the bit that, so what have we got? We've got the imaginary unit here, I, square root of minus 1. Imaginary numbers play an important role in quantum mechanics. H bar here is the reduced Planck's constant, h over 2 pi, with units of energy multiplied by time. And then we have this quantity here, h, which is called the Hamiltonian. Let's write that down. So h is defined as follows. It's a differential operator. We have this nabla squared in here, which we can expand as follows. So it's just the partial derivative with respect to x squared plus that of y squared and that of z squared, remembering the notation from the last board. And if this looks confusing, just remember this is always acting on psi. So this term here, dx squared acting on psi, is really just psi double prime. Okay, so it's called the Hamiltonian, and it's what's called an energy operator for the system. So the Hamiltonian acting on psi is going to return the energy of the system, as we'll see in a second. In general, specifying the Hamiltonian specifies the entire quantum problem we want to solve. So when we write down a quantum mechanical description of a system, we just need to write down the Hamiltonian. And in fact, this first term is fixed. What we need to specify is the potential of the system, which is much like what you do in classical mechanics as well. So the potential we will assume in this course is time independent. It doesn't need to be, but we won't consider time-dependent potentials here. Okay, so let's take a look at attempts to deal with how to solve this equation. So the time-dependent Schrödinger equation, where I've written it with psi dot this time, is a separable equation. What we mean by this is that we can substitute the following ansatz. We can say that psi of x and t is equal to, and let's treat it in 3 dimensions in general, is equal to phi of x only and t of t. So these are 2 separate functions, one which is only a function of time and one which is only a function of positions. When we substitute that ansatz in, we see that the equation reduces to the following form, where the phi has pulled through the time derivative because it's not a function of time, and this is a partial derivative. The partial derivative of t with respect to time is actually a total derivative because it's only a function of time. And over here, the Hamiltonian, because the potential is time independent, the Hamiltonian only acts on the spatial coordinates, so we can pull through the t over here. Rearranging slightly, we get 2 different equations. One purely in terms of t, and one purely in terms of x. So we've turned what was a partial differential equation in terms of both x and t into 2 separate equations. One is an ordinary differential equation in terms of time, and the other is potentially still a partial differential equation in terms of positions. So the fact that these 2 are equal for all times and all positions means they must both be equal to the same constant, and we're going to suggestively call that constant E. Suggestive because it should remind us of an energy. So let's number these equations. Let's call this one 1 and this one 2. We'll move this up to the top of the board and we'll deal with 1 and 2 separately. So first, equation 1 simply rearranges to the following form. H acting on phi is equal to E multiplying phi. And this is what's called the time-independent Schrödinger equation, because phi here is now only a function of positions, not of time. Let's put a box around it. In general, this one is very tricky to solve. In fact, in general, it's impossible to solve. Remember, the Hamiltonian here contains all the real information in the problem in the form of the potential. So, in general, we need to solve this differential equation in terms of boundary conditions, which we're going to specify, and you can see that it's an eigenvalue equation, in that we need to solve this for both the eigenfunctions, phi, and the eigenenergies, E, which will be the energies of the particle. Let's take a look at the second equation there, where I've done our favourite trick of multiplying through by dt. We can then integrate both sides to give the result. That is, the time evolution of t is simply a phase winding, a winding of the complex phase. So sticking our ansatz back together again, remember psi, the wave function, is the product of t and phi, we find that if we can solve the time independent Schrödinger equation, which by the way we sometimes call TISE, then for free we get the time evolution of the wave function, where phi of x is the solution to the TISE. So while this is in general impossible to solve, there are a set of very important cases which it is possible to solve, and those are the ones that we'll be looking at in this course. Okay, thank you for your time. It must have been very hot in the 1920s. If this suit is anything to go by, I think I'll turn back into my normal clothes. Excuse me, Jeffrey, sorry about that. So I'll see you in the next video where we will take a look at some particular solutions to the Schrödinger equation. Thank you.